Good afternoon, everyone. I welcome our today's speaker, Professor Srinivas from IMSC Chennai. And before starting his talk, let me remind you all and request you to keep your audio on mute. There will be a question answer session at the end. Nevertheless, if you want to ask any question, please use the chat box or use the raise hand feature and wait for a signal from our coordinator, Professor Shanta Leshram. Welcome, Professor Srinivas, and please.
So shall I start now?
Yeah.
So thank you, Shanta, and the organizing committee. It's nice to meet online. So, okay, so my talk is on some work of Ramanujan. So let me start by showing the first slide. See, it's on, basically it's on lattice point problems. So what is a lattice point problem? So basically it is counting the number of points with integer coordinates in a closed area. Like, so we are interested in a set of points, let's say xy, in the xy plane with xy integers. Such points form a lattice and therefore they are called lattice points. And lattice points problem is then estimation of such points inside large closed domains. All right. So classically, there are two famous problems that we know. Okay. One is called the circle problem, and that is by Gauss, which counts the number of lattice points inside a circle. And the other one is the famous Dirichlet divisor problem, which concerns the estimation of the number of lattice points inside a hyperbola. Okay. And what is Ramanujan's lattice point problem? This concerns estimation of number of lattice points inside a right angle triangle. Okay. So basically the aim of, so what we are going to do in this talk is touch upon circle problem and Dirichlet divisor problem, and then we shall discuss a little more detail in the problem of Ramanujan. Okay. So the circle problem, take a circle u square plus v square is equal to x, and then we want to find all points nm integers such that n square plus m square, the points are inside that square. Okay. So the way to do it, one of the ways to do it is to each lattice point associate a unit square. All right. And then notice that the union of these lattice points, when you take it, union of these squares, unit squares, it contains the lattice points, total lattice points. All right. So if you take a little bigger square, therefore, of radius, let's say, we have, let's say, one lattice points here, and this is a unit square. All right. So the union of all these kind of circle, the squares will contain the lattice points. On the other hand, if we take this circle, then the union of squares contain this circle. This is a smaller circle which is inside. As a result of this, what we get is the following. The number of lattice points is bounded above by the area of the bigger circle and bounded below by the area of the smaller circle. All right. That means the lattice number of lattice points, which is A, minus the area, is less than 2 pi square root of 2x. So pi x is the area of the circle, and this is a perimeter. Therefore, roughly saying that the number of lattice points inside the circle is about the area of the circle with an error of the order of the perimeter. In fact, it is true in general. Steinhaus, he proved that for any closed continuous curve J with the area, let's say F, and length of the curve L, the number of lattice points A inside or on the curve is given by the area as the first approximation, and this is the error, the length of the curve. Okay, this is true in general. Right. This is just a first approximation. Now, if you want to know better approximation, that means better error terms, which is what one does in analytic number theory, then the following is known. Okay. So Rx is now, so this is as x tends to infinity, we want to count the number of lattice points inside the circle with n square plus n square less than or equal to x. The radius is square root of x. So Gauss, as we have seen before, he proved that this error x to the power theta, theta is half. That is quite elementary, just by geometry. All right. Then in 1906, Sierpinski improved this theta to 1/3. And then Vanderkorput in 23, he said that one can take any theta less than 1/3 minus epsilon. And then Landau, Littlewood, Wallfish, they improved in the 3rd decimal place. And then Wallfish in the 2nd decimal place. And so these are the developments. All right. LK Hua finally 3 to 5. And then change in run. So finally, the latest, as far as I know, is by Ivaniak and Mojucci, which is 7/22, which is 0.318. How far can we go below? So it is known by the result of Landau and Harding that we cannot go below 1/4, because they have proved an omega result, which says that this error is bigger than x to the power 1/4 for infinitely many x. All right. Therefore, the best one can hope is 1.25, but we are farther away from that, because the best known is 0.318. A little better is known in the omega result. Gangadharan has proved that this is Rx is pi x plus omega times x to the power 1/4 log x log x to the power 1/4 log x to the power 1/4 times log x to the power 1/4. So this is about the circle problem. Now let's look at the divisor problem. All right. So this counts the number of lattice points inside a hyperbola u v less than or equal to x. So we want all integer points u and v, which is bigger than 0. We have to take bigger than 0 because we can't include the axis, because the axis have infinitely many lattice points. Okay. Therefore, the divisor problem is concerned with estimation of this dx, the number of lattice points with the axis and the rectangular hyperbola uv is equal to x, counting those, if any, on the hyperbola but not on the axis. Why can that means dx is nothing but summation mn less than or equal to x, which can also be written as summation n less than or equal to x dn, where dn is the divisor function. All right. So yeah. So how does one go about counting these lattice points? All right. So Dirichlet in fact proved that dx is x log x plus 2 gamma minus 1 times x plus O of x to the power half. All right. And it's not difficult again to show this result. All right. So one has to only look at this. Sorry. So we have this. So let's say Q and D varies here. We have this, QD. And so let's say this is, all right. So you look at the line, Q is equal to D. Now, the number of lattice points on this is symmetric about this Q is equal to D line. All right. Therefore, what one does is count. So this length is square root of x. Okay. Count the number of lattice points to the left of this line. So here, up to this. So therefore, N1, let's say N1 is the number of lattice points to the left of the line. Q is equal to square root of x. All right. Then twice that number minus this area will give us the dx. All right. It's quite elementary. Okay. Therefore, what we get is this one dx is 2 times the number of lattice point x by q, q less than or equal to x, minus, remove the area of the box with side square root of x. All right. Now, when you open up these brackets, this is x by q plus you get a small fraction, which is O of 1, minus this one, square root box, square root of x square, which gives you this much. So therefore, this is in total, what you get is 2 times x, 2 times log square root of x plus gamma plus O of 1 by x minus x plus O of square root of x, which is essentially this much. All right. So this much is pretty elementary. So what are the improvements on this problem? The improvements are as follows. So Divisor in 1849, he showed 1 by half that we have discussed just now. Wander Karput, he again 0.33, again he improved in the second decimal place. Tsung Tao and Rickard, they improved in the third decimal place. So you see the difficulty of the problem. Improving this takes so much of time, 28 to 1953. And then the next improvement comes in the third decimal place by Kolesnik, 1969. He again improved his own result. And then again, finally, Ivaniak and Mojoki, 0.318. You will see the similarity with the circle problem, because both the problems essentially reduces to estimating the same exponential sum. Therefore, they give the same result. Okay. Here again, we cannot go below 1 by 4 because we have the omega result by Landau and Hardy, saying that this alpha, the exponent alpha, has to be at least 1 by 4. All right. So any result which says that O of x to the power 1 by 4 minus epsilon is false. This is the importance of omega results. Okay. But we are far away from 1 by 4. All right. Now comes Ramanujan's lattice point problem. Okay. So as we know, the first letter of Ramanujan contains several important results. Okay. And one of them is the following. He says that the number of numbers of the form 2 to the power u, 3 to the power v, up to n is log 2n log 3n divided by 2 times log 2 log 3. All right. So rewriting this one, namely 2 to the power u 3 to the power v less than n as u log 2 v log 3 less than or equal to log n. So this again, this you see that, and let's say, let's put, just to generalize it, let's put log 2 is omega and log 3 is omega prime and log n is eta. Then Ramanujan's assertion is that the number of solutions of the inequality is approximately this one. Okay, is approximately eta square by 2 omega omega prime plus eta by 2 omega prime plus half. Interestingly, like many of his results, which contains some mistakes, this half is not correct. However, in later years, he applied much more sophisticated methods and got improvements over the results. All right. So we see that, as we have discussed in the beginning, that the number of lattice points inside a closed region bounded by a continuous curve is given by the area, and the error is order of the perimeter. Therefore, this, when we look at this when we look at the lattice points inside this, let's say, inside this triangle, and this line is u omega plus v omega prime is equal to eta, the hypotenuse. Then when v is equal to 0, you have this is equal to eta by omega, and this is eta by omega prime. This is what we do. So therefore, the area of this is given by 1 by 2 times eta over omega into eta over omega prime plus O of eta. All right. So this is the first approximation. Notice that if n, the number of solutions of this inequality is invariant under any multiple of k. Okay. Therefore, essentially what it matters, the improvement of the error can be obtained only by studying the arithmetic nature of this quantity omega by omega prime. All right, this is first observation. So G.H. Hardy, he did extensive study of this. In fact, his book 12 Lectures on the Life and Works of Ramanujan contains a chapter devoted to this one, and my this exposition is taken from there. Okay. So the number of solutions, let's write the number of solutions, number of lattice points inside the right angle triangle as so what Hardy proved is, in fact, the number of solutions is this plus error r eta, where r eta is O of eta for all rational. So when theta is omega by omega prime. So this is theta is in general omega by omega prime. Okay. So if theta is rational, then it is not difficult. It is very simple. All right. But if theta is irrational, then much better error term can be obtained, namely little of eta. And in fact, Hardy improved it to little of eta by log eta also. And in the case of Ramanujan, where omega is log 2 and omega prime is log 3, one gets the error as little of eta by log eta. So this is Hardy's analysis, Hardy's theorem. Okay. And later, Hardy and Littlewood, they found a much better error. Namely, so theta is irrational. So look at the continued fraction expansion of theta. Let's say Pm by Qm is mth convergent of theta. So if Qm plus 1 is bounded by Qm to the power alpha naught for some alpha naught, then they say that this error term R eta is O of log eta if alpha naught is equal to 1. Otherwise, it's bounded by O of eta to the power 1 minus 1 by alpha naught plus epsilon, okay, for every epsilon positive. So this is the better result by Hardy and Littlewood. Then myself, Ramchandra and Shankar Narayana, we observed the following, that if theta is quadratic, okay, then this error term is O of log eta. On the other hand, if theta is any algebraic irrationality of degree at least 3, bigger than or equal to 3, then R eta is bounded by O of n to the power epsilon for every epsilon positive. And in the Ramanujan's case, where theta is log 2 by log 3, then R eta is given by eta to the power 1 minus 1 by alpha naught plus epsilon. This is what Hardy and Littlewood got, but with alpha naught this much. They simply said some existence of alpha naught, but we were able to figure out alpha naught is 2 to the power 40 times log 3. All right. So more recently, Karthik Babu and Usha Sangle. Karthik is student of IMSC and Usha was a postdoc here at IMSC. They have obtained the following. They have generalized it much further. So take A, B any positive integers such that A and B are multiplicatively independent. So multiplicatively independent means log A by log B is irrational. Okay. Then put omega as log A, omega prime as log B, and theta is omega by omega prime. Let mu be an irrationality measure of theta. So what is irrationality measure means? So a real number gamma, say that it has irrationality measure mu, if mu is the infimum of all numbers, all real numbers rho, such that this thing happens. Gamma minus p by q is bigger than or equal to 1 by q to the power rho plus epsilon. For all q bigger than q naught epsilon. Okay. So let's say mu be an irrationality measure of theta, and take any number beta naught plus 1 which is bigger than mu. Then they obtain that the error term R eta is n to the power 1 minus 1 by beta naught plus epsilon, with beta naught explicitly like this. The values of beta naught you see large numbers, and this is the case of Ramanujan. A is log 2 and B is log 3. And in this particular, so in particular, they also obtain an improvement over this one, namely beta naught is, just 1 second please. Internet off करके बोलो, off किया था. In particular, beta naught is less than or equal to 2 to the power 18 log 3. So this in particular, this is just a one particular byproduct. What we obtained earlier was 2 to the power 40 times log 3. Now they have reduced it to 2 to the power 18 log 3. This is just a byproduct. Okay? This is just a remark. So this is the latest update on the problem of Ramanujan. Okay. Now let's look at how to count, for improvement purpose, how to count the number of lattice points inside a right angle triangle. All right. So consider the right angle triangle with vertices 0 and omega. So that's what I have. This one. So let's say this is n over omega. This is n over omega prime. This is 0, 0. Now take any u is equal to n. This is u is equal to the line u is equal to n. All right. Now the number of lattice points on this line u is equal to n is nothing but the length of the line. That is eta minus n omega by omega prime, integral part of that, plus 1. All right. Therefore, for a fixed u, these many points are there. Now vary u from 0 to from this to n over omega. Okay. That's what we do. So therefore the number of lattice points n eta is nothing but n less than or equal to n over omega. So n varies from here to here. 1 plus 1 minus n omega by omega. Now when you simplify this one, you open up the brackets. Now here, bracket of x is not just x minus the fractional part, but this famous function x minus integral part of x minus half. So it is just slightly averaged towards half. This has many nice analytical properties, but we are not going to discuss those things here. So therefore, simplification gives this sum to be n minus eta minus n omega by omega prime plus half minus summation eta minus fractional part of eta minus n omega by omega prime. All right. And therefore, this first sum is estimated trivially. All right. Notice that the first sum is nothing but the number of terms okay. So here the number of terms times this one. So let's go back. So here, so the number of terms into this one, right? So that's what we get. So the first sum gives us eta square by 2 omega omega prime plus omega by 2 omega plus omega eta by 2 omega prime. All right. The second sum is this one, the fractional part. This is what the error term. This is the error term. All right. Now, as we saw, that the estimation of this depends on the nature of theta. So what Hardy did, he looked at the n convergent of this theta. So for all irrational theta, he proved that in fact this S eta is bounded by O of n by eta by Qm plus O of Qm. The Qm is the denominator of the mth convergent. So, all right. So this is very crucial estimate. Okay. Once you have this one, then the fact that given any delta and even any sufficiently large eta, one can always find an m such that the convergent, the denominator of the convergent is bounded by below by 1 by delta and above by delta eta. This is a standard fact in this theory. And therefore, once you have this one, now the errors are bounded by qm and eta by qm. But you see that eta by qm plus qm is less than 2 times delta eta. Okay? Therefore, S of eta is bounded by little of eta because delta is arbitrary small positive number. Okay? So this is how Hardy has got the error to be little of eta. And a little bit more analysis allowed him, a judicious choice of this convergent QM allowed him to show that it is in fact little of eta by log eta. All right. And our observation, namely our remark follows from the Hardy-Littlewood's theorem. Okay. So recall that Hardy-Littlewood said if Qm plus 1 is bounded by Qm to the power alpha naught, okay, then R eta is like this. So therefore, the aim is to show this one. Okay. Now take any convergent Pm by Qm to theta. Then this is bounded by 1 by Qm times Qm plus 1. These are properties of convergence. Okay. Therefore, this implies that Qm plus 1 is less than 1 by Qm theta minus Pm. All right. Therefore, we need a lower bound for this quantity. A lower bound for this quantity, 1 by lower bound for Qm theta minus Pm of the type this one, Qm to the power minus alpha naught. So that 1 by Qm theta minus Pm will be less than, so this will be less than Qm to the power alpha naught. And then we can use Hardy-Littlewood's. So if theta is any quadratic irrational, then alpha naught is equal to 1 is admissible. All right. So therefore, for all algebraic, the quadratic, when theta is quadratic, we obtain R eta is equal to log eta. Okay. This is the proof of the first observation. Now, if theta is any irrational, take any irrational of degree at least 3. All right. So then the theorem of Roth says that alpha naught can be taken to be any constant bigger than 1. And that immediately gives, by using Hardy-Littlewood's theorem, that R eta is bounded by O of n to the power epsilon for every epsilon positive. All right. And what happens in case of Ramanujan? So in the case of Ramanujan, Feldman showed that alpha naught exists. So Ramanujan case is log 2 by log 3. In that case, this alpha naught exists, and by explicit computation, one shows that in fact alpha naught is 2 to the power 40 times log 3. All right, this is admissible. Okay, and therefore we have this theorem. We have this result. Namely, this is how we got alpha naught to be 2 to the power 40 times log 3. All right. Now, before I conclude let me tell you that, you know, from the from let me go back. Yeah, Hardy little load. So yeah, this thing is what makes, you know, in fact, study of this sum is the most crucial part. Okay, study of this S eta is the most important thing in this entire theory. So how to show that this is very small? There are lots of cancellations. How to show that this is pretty small? So how did Hardy and Littlewood, they did is they split this sum n less than or equal to, you know, just few minutes more. So what they have done is this eta is less than n is, sorry, n is eta by omega in this sum. All right. So they did a very wonderful, clever trick. So since n is an integer, so you look at eta by omega and write it as in terms of the denominator of the convergent. Let's say Pm by Qm is a convergent, then Rq plus S, where Q is equal to Qm. Okay. So this tells you that this is S is less than Q. All right. So they split this sum into several sums. So therefore this becomes, this sum is same as, you have this n is equal to 0 to Rq minus 1. Okay. And then we have this n by eta by omega minus n theta plus the one corresponding to this last S, that will give you simply OFS. All right. Yeah. Now this sum is what is evaluated again by looking at n is equal to mu q plus mu, where mu is up to, so mu is 0, 1 up to r minus 1, and our mu is 0, 1 up to q minus 1. Okay. So this again split into, this sum is split into subsums, and then one shows that in fact those subsums are very small. The total add up to little of mu. This is how this is how Hardy and Littlewood they obtained. So this finally this adds up to O of eta by q. So we have an eta by q coming from this, and this O of S is same as O of q. And that's how they get this S eta is O of eta by Qm plus O of Qm. Why I stressed on this is that from this only, you know, all further developments came up. Namely, by choosing a convergent of this type, one has, Hardy has shown that in fact this is much better than this. Namely, this is little of eta by log eta. And similarly, in Ramanujan's case also, Hardy has shown, Hardy and Littlewood, they have shown that it is little of eta by log eta. Okay? So these are some of the analysis of that problem, and what is the final. Oh, got disconnected.
Yeah, your screen is gone.
Oh, wait. What happened to my screen? Is it 1 second? Oh, my net is gone. Is it? Okay, so final remark. So therefore, these are the developments that has happened so far. Finally, recently, as I mentioned, Karthik and Usha, what they did is they used a result of Gulio, which gives a lower bound. I mean, which deals with the linear forms in logarithms. So it gives a lower bound for certain quantity, and also the concept of irrationality measure as defined before. And they look at the theta, they study theta very closely for various values of omega and omega prime. So for various log A's and log B's, all right? And that's how they obtain explicit constants alpha naughts in each of the cases, all right? I don't want to discuss their method here because it's a recent result of them, and I came to know that it has been accepted in proceedings of mathematical sciences. I hope they will give a talk on this sometime. So I think I will just conclude this talk with this, that, Ramanujan's thing is still, I mean, as we know that several problems of Ramanujan which are open, and there is a lot of food for thought for us. So I encourage younger students to look into some of the problems of Ramanujan. There is always something to be done, and here is an example of that. So with this, I think I will stop my talk. Thank you.
Thank you, Professor Srinivas. Any questions? You can unmute your audio and ask.
So Srini, can you show the result of Usha and Karthik? Or is it not easy to show? Yeah.
Ustolj and this thing? Baker? What? Which one? Usha. The result.
Usha, yeah,
oh.
Usha and
Yeah. I will. Yeah, here is. So it will take some time to load, I suppose.
Okay, thank you.
Any question? So if there are none, you can unmute your audio and thank Professor Srinivas for a nice talk. So thank you, Professor.
Thank you very much.